So dear students, in this video we are going to study a new topic, that is electric flux. So the definition of electric flux is the number of electric field lines crossing a unit area. So here is my electric field lines. Let us consider some electric field lines this way. And there is some unit area whose plane is perpendicular to the direction of these electric field lines. The plane of this area is the surface of this area is perpendicular to the electric field lines. Let us give some direction to this area. For this concept, to understand this concept of electric flux, we will give area some direction, and we consider area to be a vector quantity. So if I make a outward perpendicular direction this way, this direction is the direction of the area vector, which is represented by A vector. So A vector is directed towards this direction and its magnitude is simply A. The value of the area is A and its direction is directed towards this direction. It is, in other way, it is also represented this way. The magnitude of area is A and this outward direction is represented by some normal direction, n cap. N cap is nothing but it is this outward direction. So in this case, if we see, if this area vector is parallel to the electric field lines, then we can see all the electric field lines will cross this unit area. Then we can say that the number of electric field lines crossing this unit area will be maximum in this case. So in this case, electric flux, that is the number of electric field lines crossing this unit area, will be maximum because this surface is perpendicular to this electric field lines, or the area vector is parallel to the electric field lines. That means in this case all the electric field lines will cross this unit area. That means electric flux in this case will be maximum. Electric flux in this case will be maximum. Let us consider another case. This is my electric field lines. These are my electric field lines. And now, if this is the perpendicular line, now if I rotate this particular surface area by 90 degrees, then what will happen? This particular area will be flattened this way. This area will be flattened this way. Now the surface of the area and the field lines are in the same direction. Or if I give a direction to this area vector, then it is directed towards this direction. This is your area vector, which is nothing but E n cap. Now in this case, the surface of the area and the electric field lines are parallel, or the area direction of the area vector and the electric field lines directions are normal to each other, perpendicular to each other. So in this case, no electric field lines will pass through this particular area. No electric field lines will cross through or cross inside this area. In this case, all the electric field lines cross inside this area, but in this case, no electric field lines will cross inside or cross through this particular area. That means in this case, the number of electric field lines crossing the unit area will be minimum or zero, basically zero in this case. So electric flux will be in this case it is 0, and which is minimum for this case, and which is minimum for this particular case. Now again, I want to do some intermediate condition also. If this is condition 1, this is condition 2, and let us do some intermediate condition. These are my electric field lines in the same manner. These are my electric field lines in the same manner. And suppose this is a perpendicular line. Now if I rotate this particular area, not by 90 degree, if it rotated by 90 degree then it becomes flat like this, but if I rotated it by some angle less than 90 degree, then it takes the shape this way. So this is your area, and its direction is this way. The area vector is directed perpendicular to the surface of the area. I can write this as well. Now in this case, all the electric field lines will not pass through this particular area. That means the number of field lines crossing will not be maximum in this case, but some of them will cross. Definitely, some of them will going to cross definitely. That means the electric flux would also not be minimum in this case. So only the few electric field lines will cross through this particular area. That means in this case, in this particular case, electric flux will have some intermediate value, not minimum, not maximum. So these are my three cases. This was my first case, perpendicular case. This was my flattened parallel case, and this is some intermediate position case. Now I rotated this in first case. I rotated this particular area by some 90 degree in this case. And in this case I rotated this particular area by some angle theta, which is less than 90 degree in this case. So what you can see is, in some cases the electric flux becomes maximum, in some cases electric flux becomes minimum, and in some cases it has some intermediate value. And if you see, in all the cases here, the direction of the electric field lines and area vector are parallel. Here direction of electric field lines and area vector is perpendicular to each other. In this case, the electric field lines and area vector are parallel in same direction. In this case, electric field lines and area vector are perpendicular to each other. And in this case, electric field lines and this area vector has some angle. This is the direction of electric field lines, and this electric field lines and this area vector has some angle theta degree, which is less than 90 degree. So what strikes in our mind is, we can write this three particular cases in a mathematical form. So the mathematical form for this electric flux is particularly, as you can say, it is a dot product between the electric field and the area vector. So mathematically I can write electric flux which is represented by phi, and it is a scalar quantity. So this phi, so we can represent this electric flux as a dot product of electric field and area vector E dot A. Now since it is a scalar quantity, so E dot A will be EA cos of theta. So this is the value of electric flux, or mathematical representation of, electric flux. So you can clearly see in this case, first case, electric field and area vector have zero angle between them, because this and this are parallel. That means they have a zero angle between them. So cos 0 will be 1 in that case. So phi will be, in the first case, E and A have theta is equals to 0 degree in the first case. That means phi will be EA cos 0 degree. So phi will be just EA, which is the maximum value of the flux possible. In the second case, in this one, E and A are normal to each other. E and A, between E and A, theta is 90 degree. That means phi will be equals to EA cos of 90 degree. Therefore phi is, cos 90 is 0, so phi is 0 in this case. That means no electric field lines crosses through this area. That means flux is minimum in this case. Similarly, in the third case, between E and A, we don't know what is the value of the theta here. So we can give some general value of theta as like theta is equals to capital theta. Then phi will be equals to EA cos of theta in the third case. Since the maximum value of cos theta is 1, which we have taken in this case, minimum value of cos theta is 0, which we already taken in this case. Now between 0 and 90 degree, this theta will have some intermediate value. Between 0 and 90, it has a value between 0 and 1. That means phi will have some intermediate value which is neither minimum nor maximum, less than maximum and more than minimum. So at any other angle, theta will have some intermediate value, flux will have some intermediate value, as in this case. So this relation is all you need to understand in this particular case. That is, flux through any surface will be EA cos of theta, where theta is the angle between electric field and area vector. Thank you very much.